Sir, shall we start?
Yes, sir. Yes, sir. We can start.
Okay, sir. So welcome back once again. So we have completed step one. Step two, we are not specifically dealing with it. We assume we have done the software level implementation and we have verified and gone through the working functionality and principle of the algorithm. Next, we start with RTL design. RTL design is we have seen in the section one, all the specifications. I have explained the scrambling algorithm, everything, and we have modeled in MATLAB, right? And then that we try to map it into the hardware. We want the same functionality to run on a dedicated hardware. And in the explanation, we have seen moreover, the actually the overall hardware architecture looks like this. So this is some one black box. Any hardware generally has one clock signal and it has one reset signal, and there is one start signal. Uh, it looks for one starting pulse to start. Actually, this we are dealing with pseudo random binary sequence generator. And here we need to give the C underscore init initialization value. This is a design which I have done. This I will be showing it to you right now. Uh, just a minute, hold on. Okay, this is a PRBS generator, and here we are getting the scrambling sequence, that is CN, and once this sequence is generated, we will get an output signal called done. Why? Because as I told you earlier, once we start generating the sequence, we will get only the sequence after 1600 iterations. So if you assume like each iteration is carried out in one clock cycle, we will get it approximate after 1600 clock cycles. So we have a running clock. So after 1600 clock cycles, we start to get the actual this sequence, and we need to tell what is the length of that sequence, that is n. So since we are in our case we are assuming like our code word is 8-bit, we also need a sequence of 8-bit, but this is not fixed. Actually, as per the standard, that code word can have a variable size, so that size you need to denote, that is n, but internally I set that size to 8, so output you will get from C0 to C7, total 8 bits. So this is how the top level, high level architecture looks like. So inside this generator now, whatever we are talking about, it basically consists of two linear feedback shift registers. Uh, so this is X1 and this is X2, and the X1 is directly initialized like as we have seen, all zeros followed by at the end 1. X2 is initialized like C underscore init that we are going to send here. If you want, in your design, you can also develop a hardware for computing CNIT, because CINIT is a function of NID and RNTI. These are the two network parameters. So actually have we have seen the equation, right? Here on top, CNIT, this one. If you want, you can implement a hardware for this also. And through that our hardware, instead of sending CNIT, C initialization value, you can send NID and RNIT value. Based on that, CINIT will be calculated, and that will feed into your generator. So here you can develop your own another hardware block. But in order to avoid that much complexity, in order to keep it very simple for the sake of this today's presentation, uh, I didn't develop any hardware for CINIT. I'm directly using the CINIT value as an input. That value I'm calculating manually by using this equation as we have seen. So internally, if you look into the PRBS generator, it generally comprises of two linear feedback shift registers. After 1600 clock cycles now, we try to output the first 8 bits of X1 and X2 sequence. And internally, what we have done is like we have XORed it, and from here we get the CI. So I'm not going into much details of the internal hardware. So the internal this hardware architecture, everything, how it is built at RTL level, that we call it as register transfer level, by using what, that is like HDL. HDL stands for hardware description languages. So we have wide variety of HDL languages like Verilog, VHDL, and so on and so forth. But today's presentation is also out of the scope of RTL design, because the code is pretty large, and if I start explaining the code again, it will be confusing for the audience who don't have prior exposure to Verilog. Actually, I have developed in Verilog. So it will be like a quite a confusing. So people who are interested in hardware design now, they can learn either VHDL or Verilog of their choice. For me, Verilog seems to be pretty easy and simple when compared to VHDL. So if you can learn these algorithms out of your, sorry, these languages, like just like MATLAB and C, you have to learn. This is like for software programming. This is for hardware design. So if you learn these languages, you will come to know like how to design combinational circuits and sequential circuits. So digital circuits, uh, how you can design at the RTL level, register transfer level descriptions, so that out of those descriptions, if you try to synthesize, implement, and you do generation and everything, the original hardware can be realized on FPGA. So this I'm leaving to the audience and participants. So as of now, for this tutorial, we will only deal with the generator which I have, pseudo random binary sequence generator, which I have generated, which I have realized in by using Verilog language. So now you all can treat this as a black box having some set of inputs and set of outputs. We will work only at the top level, that is high level. We are not going into much details about internal architecture. Of course, as per the equations, we come to know like it uses linear feedback shift registers, LFSR, and at the end we need one XOR. These are the minimal hardware details, but we do also have some controller inside it. Why? Because we need to know how many times the shifting operations needs to be done after 1600 shifts. Now we start to output the data. So some glue logic related to controlling and the data path, those all are integrated into the hardware. So that is quite complex as per the current lecture and the given time constraints, that I'm skipping it. So we just as I have designed the block, we will take that block and try to build a circuitry around this in order to implement our actual task, that is 5Z physical layer processing on FPGA in terms of a scrambler circuit. So this is our main objective, right? So that's why we take this generator and try to build a circuit around this, and we see how the implementation is being carried out on an FPGA. So this is our main motivation. We stick to it. So we assume like the RTL design has been completed. Once the RTL design has been completed, we do some functional simulation. We do verify whether our hardware is working as per the intended functionality or not. If at all, if there are any bugs, if it is not working properly, then from the functional simulation, we go back again to the RTL level, and whatever the identified bugs are there, we try to resolve all those things, and again we do verification. So once the functionality is being matched, this functionality matching of this functionality in the sense you also you have priorly run implemented this one in software level, right? Algorithm development in MATLAB or C or Python. By under similar parameter constraints conditions, the architecture should output a known sequence for a known set of input. So we will check with the known set of inputs and known set of outputs at and compare both at the software level and the hardware level. So when once these both are matching, then only it is an indication like whatever the hardware that we have described in the RTL, that is Verilog language, is valid. Then only we proceed to the next steps for implementation, because if this stage itself there is some bugs, then there is no point in implementing on FPGA. Why? Because of obviously the circuit will not work as per the intended functionality. So this is a functional simulation is a very key step. uh, I have verified this functionality for the time's sake. These are all. This is also we are trying to neglect it. We straight away proceed with from step 5 onwards. So assuming like once we have designed everything, now how to implement it on FPGA, how to test it, those all we can. I will try to show a brief demonstration in the coming presentation. So I think up to here it is very clear to everyone. So now let's make a deep dive into the actual fun part that we are looking for, the hardware implementation. So for this purpose in the tutorial, I'm using Xilinx Vivado 2021.1. You can use any version of your choice. So I will just go walk you through all the steps. Main important steps uh, that are in the FPGA design flow that we need to follow for doing the hardware implementation. So once you open your Xilinx Vivado, this is the landing page. And from this, you just click on create project. So a wizard will open like this. Next, you select a path to your project. My path is already set to D drive ATAL FDP NAC. Since I'm writing a HDL, I kept a folder called HDL. Okay. And today I'm creating a project called live underscore demo. So whatever the project files that will be stored in this directory. Next, it is asking to type the select the type of the project. I'm selecting it as like RTL. Now the important thing is like you need to select the board. Ultimately on which FPGA development board you want to implement this, that you need to select. And on with me, I am having a Xilinx Z board. I will turn on my camera. Yes, you can see, right? I don't know it is visible or not. This is a board I'm having right now with me. This is called Xilinx Z board. I will show it in the website. Uh, you are able to see in the camera, right? Can anyone acknowledge? Hello? Hello? No one is listening.
Yes, sir. Yes, sir. We are able to see that screen, sir.
Okay. Okay, not the screen, camera.
That camera,
I'm
yes, sir,
showing the board.
in front of FPGA board.
Yeah. Okay, okay.
Yeah.
Thank you. Yeah, this is the board that we are going to use today for the implementation. You can search on web as well, like Xilinx Z board. Yeah, this is the board I'm talking about. Yeah, this one. So this board I'm going to use today. So this board has one specific number. It falls under general purpose category. Family is like Zinc 7000. Package is like CLG 484. Speed grade is 1. This is the part number. XC7Z020 CLG 484 minus 1. So once you purchase a board, on that it will be returning the part number is available. So you can select that part number, click next and click finish. Now the Vivado will manage the project. It will create all the initialization files in the respective directory, and this is the landing environment. So here you have many panels and windows which will help you in carrying out the FPGA implementation. And our task is like 5G physical layer processing on FPGA. And specifically, we are focusing on implementing a scrambler circuit, scrambler block, or a scrambler component of a 5G communication system on FPGA. So for that, we need to proceed with RTL design. So here you can see there's no design. This is completely empty. So you need to start from scratch by using Verilog HDL language. You need to write the specifications and descriptions of your hardware as per the intended functionality. So for that, on the left hand side, you can click on add sources and you can select the design sources, add or create design source. So basically I am adding the source because I have already generated, because it takes a long time to design the RTL description. So for that I will try to make use of my existing. Yeah, the name of my file is prbs underscore generator.p. So I'm just adding it. So my design file has been added. Actually, in your case, what you have to do, you have to create a file and then you have to write the description in the RTL level. So I'm not disclosing the code right now. Why? Because it is out of the scope of the current presentation. Maybe you can just look at the top level entity. Top level entity is this one. So it has clock, it has a reset, it has a start, it has C initialization sequence. This is a bus of 31 bits. So we need to send a 31 bit data. Clock, reset, start is a single bit data. And C out, that is n bit data. So in our case, we are taking scrambling sequence of 8 bit. Why? Because our code word or a message data is also like 8 bit. So this can be variable. Here you can change it depending on the requirement. And done is the indication like the computation is completed and the code has been generated. Once the code scrambling sequence is generated, then only you need to use it for scrambling the data, because it takes, as I mentioned, like initially it will take 1600 clock cycles or latency to generate the sequence. So without the sequence is generated, you cannot perform the scrambling operation on the data. So before the data arrives, you need to set all these parameters and run your generator and compute the scrambling sequence. Once the sequence is ready, then use that sequence. Use the sequence will be like constant for the all the number of code words or the message will vary, but for a particular device, using that device you can send many messages, but for each message you will do scrambling using a same scrambling sequence. Maybe for the another device only you will change the scrambling sequence. So scrambling sequence will not change. So with only with respect to the whenever there is a change in the equipment, whenever the uh, your the communication in the communication system, it is switching between one user equipment or another user equipment, then only there will be a change in the, or you maybe you at the time of allocation of the channels or these things. I'm not going more into more details of those things. So these are the minimal things that you can just focus on. So this is a block. So imagine that you have generated all the block, then this is like Verilog code design file. So once the code has been done as per the FPGA design flow, you need to do functional simulation. That is a fourth step. So for functional simulation, what you have to do, you have to verify the logic correctness of the RTL code using test benches. So you need to write a simulation test bench. So for that, again, you click on add source. Instead of design source, you have to select simulation source. And here you have to add an existing one or else create a new one, a test bench. And in the test bench, you have to uh, include this design file, and you need to do simulation, and you need to check whether the design is working as per the intended functionality or not. In that way you will check, but right now we are skipping this step. Why? Because I have already verified it, because we are running short of time. If time permits, I will just show you how to do functional simulation. So after that we will do finally like synthesis. So once our RTL is description is ready, uh, RTL description is like a language, right? So we have some for one circuit. Now we have written one big line of code. The code consists of descriptions. Now this has to transform into a circuit. Circuit is like a combination of gates. I'm just drawing some random gates, maybe flip-flops, so on and so forth. This is like circuit level, right? So this is a data or description or language you are writing, like maybe in this data as per the language you have, if some condition begin and like, or else some case, and at a clock edge what you need to do, some statements, how to drive the output lines. These all you will describe in terms of language. So for that you will have language templates. We call it as template. There will be some styles will be there, like coding styles. With that you will write. Ultimate goal is to write. Ultimate goal is to get a gate level realization, that we call it as netlist. So how to transform this description into gate level netlist? Now this we call technically as synthesis. So it is the uh, it is the responsibility of the designer, right? Whatever the descriptions that he is writing, ultimately it has to transform in the form of a circuit. He has to finally get a circuit. So for that purpose, he will be doing the synthesis. Uh, so the thing is like, is our circuit ready? We have not completed our design. The design is not yet ready. We have to make the final completion. So for that purpose, I'm just creating a blog design. Don't worry about all these concepts. So it will be a little bit easy only if you can pay some attention. Uh, for the sake of understanding, I'm doing the design using block level based design approach. Actually, we need to make the hmm, top level design. Actually, our main goal is like scrambler, right? In this scrambler, what is available is like pseudo random binary sequence generator is available, and from this we are getting the C of n. Maybe from another source we are getting the message bits B of n. These two we need to do XOR, and we need to output it to like B bar of n. This is our circuit. And what is our main interest is like we are generating this sequence. We try to observe this sequence. We are giving one message signal. We try to observe this message, and we are getting this scrambled sequence B bar of n. We try to capture that, and what we do is like to this scrambled sequence. Again, we add one more XOR, and what we do is like we take the same scrambling sequence C of n and try to get our original message signal B of n. So this is a circuit I am trying to build right now on FPGA. So this I have drawn in the form of a block diagram. So what I will do is like, so first I add my generator. Okay. So as I told, right, my generator uses a clock signal. Since it is a sequential circuit, we have a clock because the linear feedback shift registers also operate with respect to clock. On every clock edge now, it will do the shifting operation, and it will generate the C of n sequence. So basically it's a sequential circuit. I'm using a clock. So this clock now I am connecting it to a clock circuit that is called maybe like a PLL on FPGA. So in order to do that now, there is available IP core in Xilinx Vivero that we call clocking wizard. So maybe assume like in our design specifications, there is a constraint called you need to operate clock at 100 megahertz. So now consider this as one of the design criteria. So what I'm doing is like I am generating a 100 megahertz clock. I'm leaving all other clock parameters to be by default. Okay. So this clocking wizard also has one clock input, right? That goes to the onboard crystal oscillator. So that's why I'm making it like an external pin. This I'm naming it as clock. Because this FPGA board, whatever I'm having, right? This also has one onboard crystal oscillator that works at again 100 megahertz. Maybe you can convert that 100 megahertz to 50 megahertz also, no problem. 50 for your understanding I'm showing. So let let us operate at 50 megahertz. Let 100 be our onboard oscillator. Next, there is a reset signal. This also we are providing it from the external. For that purpose now, on this FPGA, you can see there are some push buttons over here. I'm configuring that as one of the reset. So I will show you at a later stage, like how to assign the pin numbers and those things. But as of now, I'm just making these external connections. So to my clock wizard, I'm getting an onboard crystal oscillator clock, And through my onboard, I want to configure one of the push button to be as a reset. This is like active high reset, uh, but the clock main circuit that is operating at active low reset. You can see a bubble at the reset pin. So how do I get a active low reset? But here I used an active high reset. But clocking wizard now, as it's a PLL clock, it's like phase locked loop. Once the clock signal is stable, it will generate a locked output. The locked output will be like always active high. So when the clock is not stable, at during the transition time, I want my circuit to get reset. At that time now, the clocking wizard give outputs the locked output as like active low. So this I can use like active low reset. So clock output 1 is connected to clock. This locked, I'm connecting it to reset. Yes, this is fine. Next thing is like here to the PRBS generator, we need to give start input and see initialization input. Start input in the sense I told, right? So once you give a start pulse of short duration for approximately TC time period. TC is in nanoseconds, TC nanoseconds. TC is nothing but 1 by FC, that is the operating frequency of the clock. So in order for the pulse to be visible, at least it should have a width, minimum width of TC nanoseconds. So this short pulse is required in order to trigger our generator. Once the generator is triggered, what it will do, it will use this CINIT value for initializing X2 sequence. X1 sequence is by default initialized to 1, that is 31 bits of 1. That means the last LSB bit is 1, remaining bits are 0. This is automatically initialized, and X2 will be initialized by this external input called CINIT. 30 down to 0 means 31 bits. So 30 down to 0 means total 31 bits are there. This we are providing from the external. So the algorithm, the circuit will work as per the algorithm. It says like after 1600 clock cycles, the iterations continues progresses plus another 8 clock cycles. Why? Because it has to output our 8 bits of uh, scrambling sequence, right? This data is also in the shift register. So again, for another 8 clock cycles, it has to work and it has to output this 8 bits through the output. That output will come here. So that's why Cout is like 7 down to 0. 7 down to 0 is nothing but total 8 bits. So the thing here is like, now how to give these inputs. So manually giving these inputs at clock period. See, our clock is running very fast. We take like 50 megahertz, right? That means TC is equals to like 20 nanoseconds. As soon, this is our clock, right? As soon as one start pulse arises, the generator starts computing it. Before this start arises, now you need to give your CINIT value. CINIT value you need to pass. This is like start. This is like clock. And this data remains stable all the time. So once the start comes, it uses whatever the data on this line, that is CINIT, and starts computing the CFN sequence. But to give the data is like 31 bits. 31 bits, right? So, but if you look into this FPGA development board, now here, only 8 sliding switches are there. With these 8 switches, I cannot give 31 bit data. Because sliding switch, if you slide the switch up, it will be like logic once drop the switch, it will be 0 like that. On the FPGA development board we have only 8 switches. So manually it is very difficult. Why? Because we don't have those many switches on the FPGA. So how we can view? We can view virtually. Because this is our FPGA, right? We are programming our FPGA using JTAG cable. By using these cables only, we will be adding debug cores. These debug cores will enable to pass on inputs, capture outputs to and from FPGA. So this is a setup. You have your personal computer to this personal computer over JTAG interface. You will connect your FPGA. Whatever the hardware logic that you have developed, that data will be there. That data we call it as bit stream, or we also call it as configuration file. This configuration file will put it in the FPGA. Then on the FPGA, our hardware circuit will be realized. Again, by using the same this JTAG cable, we will pass the data from the PC to the FPGA as an input. Whatever the data coming out from the FPGA, again it comes via through the same cable to the PC. So to enable this feature now, we have some debug IP cores in Vivado. One is called VIO IP core, that is virtual input and output. Another one is called ILA, integrated logic analyzer. In our case, we are only using VIO. ILA I'm not using here to reduce the complexity. So through VIO, we will send the data. So now here, if you look, we have to give two inputs, right? So first, yeah, from the library, I'm taking the VIO. So this is my VIO IP. So clocking wizard clock generated output is connected to clock input. Now look, this is the VIO. It has some set of inputs and outputs. You can upscale it or downscale it as per your choice. Input ports, output ports. You can add number of ports here. Maximum 256 input ports and 256 output ports you can add. So let's see. You need to pass inputs to your generator. Pseudo random binary sequence generator. To this generator, that is start and this one. You are passing inputs, right? So that should be the output of the VAO. From whatever the VAO outputs, that only can enter as an input to the generator. So we need to scale the number of outputs. For the time being, we require two outputs for the VAO. That is for one to control the start, another to control the CINIT. So start is of 1 bit, CNIT is of 31 bit. So double click on this to get the IP customization menu. Number of output probes. By default it is 1, but we need 2 output probes. And we need to customize the width of each probe. So for that you go to probe output port section. Here probe out 0, I'm setting it to 1 bit. Probe out 1, that is I'm setting to 31 bit and click OK. Now you can see here on the VIO side, output side, you got two ports. One is 1 bit, another one is 31 bit. So this one I want to use it as a start. So I'll connect it. This one I want to use it as CINIT initialization. Once I rearrange this logic, so this is how it looks like. So from the VIO, I am giving the inputs to my pseudo random binary sequence generator. You please note down all these things. Why? Because at the time of visualization, you need to remember these probe names in order to check real-time data from FPGA. So probe out 0 connected to start, probe out 1 is connected to CNIT. So the pseudo random binary sequence generator is configured. Now, if you check, so here, forget about other parameters. We are generating 8-bit code word and we are running iterations up to 1600 as per the algorithm. These are other parameters that you can forget it. So the next thing is like, so once you pass on these things, actually, sorry, we made one mistake. This start should not be connected directly. Why? Because as I told you, right, start should be like a single pulse of minimum width TC nanoseconds. But if the start is continuously high, what will happen? The generator will keep on running. It will be in the continuous running mode. Actually, this is TC nanoseconds, right? We need to give only one pulse of TC nanoseconds. That is like 20 nanoseconds duration. Suppose, imagine that you are configuring a push button on the FPGA. There is a button on the FPGA. You are configuring it to give as a starting pulse. But if you press and release in the order, we can only give inputs in the range of order of seconds. You press and release, maybe the switch is pressed for 1 second. It is not pressed for exactly 20 nanoseconds. So you end up of giving a continuous long, either you end up in giving a logic high value or a pulse of very large width. What this will create? This will create a generator to run continuously beyond the intended functionality. So once it runs beyond like an infinite loop, near to infinite, not infinite, but ultimately you will remove the pressing of the button, right? Maybe for a long duration, maybe you need to get a code word like 10101100. But instead of getting this, because this you will get if you run exactly 1600 clock cycles plus 8 clock cycles, then only you will get this. But if you run either 1 clock cycle less or 1 clock cycle more, you won't get the same code word. But you are in your simulation, in your software based implementation, when you have implemented this algorithm, and if you have run, then your software based model will say like code word should be this, like 10101011 for given set of parameters for a constant CINIT value and so on and so forth for one particular configuration. But if the start is continuously pressed, the linear feedback shift registers will run continuously and it generates another random data that don't match with the expected output. So here a mismatch will happen. So how to give a short pulse? Again, for this, you need to write one more HDL logic. Maybe suppose you are configuring a button, a slide switch or a push button on the FPGA. Even though if you press the button high for an infinity number of clock cycles or infinity number of time or in T seconds, it will still generate only a single pulse of 20 nanoseconds duration and it will stop. So you need to generate that particular hardware. So I have already generated that. So let me add that into my sources. That is called as pulse generator. I'm just adding it. It will come into my design sources. Once the pulse generator is added, you can just right click and click to add module to the design, block design. So again, if you see my pulse generator, it has a clock input. So this I'm connecting it to the derived clock. It has a reset that I'm connecting it to the derived reset signal. And here there is one trigger input. To this trigger input, I am connecting the VIO output. From the virtual input output, from the virtual switch, From the virtual switch, I set logic to 1. That means a continuous high. As soon as ideally it is at low, and this is like continuous high, and here the clock signal is coming like this continuously. As soon as there is a transition from 0 to 1, my pulse generator will generate a pulse exactly of 1 clock duration. And even though the start is high, there will be only a single pulse. So this is how I have designed. So that's why what I did is like from the VIO, I will set 1 bit to be high. That will generate a trigger. Then upon receiving the trigger, it will generate a short pulse. This pulse now I give to the start. Now my generator is safe. It will receive only 1 pulse irrespective of the pressing by the user, irrespective of the button pressing by the user. And then my generator is configured to generate the sequence properly. Now we want to check the scrambling sequence. So for that, it has generated the scrambling sequence, right? Once when we will come to know it has generated, once done is high, it is indication like scrambling sequence is generated and the sequence is coming at the output of this generator. So we will check whether done is making a transition from low to high, like 0 to 1. This is done signal. This we need to check. Once this done is high, then whatever the data that is on the output line, that is our scrambling sequence. So this is the output that we want to visualize it. So to visualize it, again, I'm using the VIO. I'm redirecting these outputs as an inputs to the VIO so that within the VIO interface, I can look all these outputs. Why? Because this done, if I want, I can redirect it to a LED, onboard LED on the FPGA board. So once done is high, that LED will glow. That will give a visual indication. And this C out is like 8-bit. So I think 8 bits, 8 LEDs are available. I can connect this to LEDs to check the scrambling sequence. Imagine like this is also like 32-bit or 64-bit or 100-bit. We cannot connect to those many LEDs. Why? Because those are not available on the FPGA board. So the obvious possibility is like we have to connect to a virtual environment where we can actually see the signal in real time, either in real time or the near real time. I'm not saying it's like exactly the real time. Why? Because first it will capture and it will store and then only it will show you. So it's like near real time approximately. So what I do, these outputs, again, I'm redirecting to this VIO interface. I anyhow am having one VIO interface. That's why within this VIO interface, I will redirect it and I will check it, all these things. So first I'm interested to check done input, done output, after that C out. So these outputs must be connected to the VIO as inputs. So I need here only one input is available currently. I need to add one more input. So again, double click it. Here you can see general options. Input probes are 1, that I'm making it to 2. And go to input probes. Done is like 1 bit. That's why I'll leave it to 1. First probe. Second probe, I will make it to 8 bit. So this done, I connect it to here. See out, I connect it to here. Now from this, we have completed the interconnections to one particular extent. Now what we have to do is like we got only the scrambling sequence. Now if we give a message bit, we need to calculate the scrambled output. So for that, as of now, we have generated C of n. Now we have to give B of n. These two we have to do some XOR operation to get B bar of n. This is our scrambled data. So for that purpose, what we have to do is like, anyhow, I'm visualizing the scrambled output.
Sir,
Yes,
sir,
sir.
sir, is it possible to wind up within 10 to 15 minutes, sir? 10 to.
Yes, sir. In another 10
Yeah.
to 15 minutes, I'll wind it up.
Yes, sir. We can wind up. Yes.
Uh-huh. Okay, so now what I do is like, there is another IP core that is available, that is utility vector logic, that I configure it as like XOR and set the size to 8 bits. So here what I'm doing is like C out that I'm sending as in second input to this XOR, and fine. And to the first input, I need to give the message. Again, that message I want to give via the VIO interface itself. So from VIO, I need to add extra output probe that can drive the input of this one. So now the existing output probes from, I need to increase from 2 to 3, and newly added probe, my message is of 8 bits size. So I set the bus width to 8. Now this message directly comes here. Now this is the scrambled output. This scrambled output, again I want to check it in the VIO itself. So for that purpose, in the VIO, I need to add one more input, and input probe, I need to set this to 8. And this one connected to here. This is scrambling. And we also need to make sure like do the inverse and check. Actually, the inverse operation will be done at the receiver, but we will check it here itself whether we are able to recover the message or not. For that, again, we need one more XOR. So this is an XOR of 8 bit. Now to this one, what I'm doing is like I am connecting the scrambled output. This is a scrambled data, and the scrambling sequence I have to give as a second input. This will be like recovered message. This should be equal to the original message or the code word that you are sending. Again, this I want to visualize VIO as an input. So input port, I need to add one more additional port. So input, I'm adding one fourth probe. In that fourth probe, again, I'm setting the size to 8 bits. Okay. And this I connected to here. Now this completes our entire hardware implementation design. So here we are having our pseudo random binary sequence generator. To this we are providing all the necessary parameters. It is generating the uh, scrambling sequence, and we are sending the message bits, and we are getting the scrambled output. And that scrambled output, again we are passing it to another XOR operation, again giving the same scrambling sequence to recover our original code word. And these all are integrated to some VIO interface, where from the FPGA we can just tap these lines and check how it is, how the signals are varying, and whether the implemented circuit on the FPGA is working as per the intended functionality or not. So once this block design is ready, you click on validation. Now the validation is successful because I have not left any ports unconnected. So once the validation is done, you need to run the synthesis. You have to click generate output products. After that, you have to create a top level HDL wrapper. As I mentioned, this is the top level of our entire design, right? The top level will be created. After that, we will do synthesis. So this is a fifth step. What we are talking about, synthesis. It will convert the RTL code. Actually, here we use blocks, but these blocks are internally having code, RTL code. That code will be converted into gate level netlist. After that, we will do implementation. resources on the FPGA. There are plenty of resources on FPGA. So the tool will automatically map to the most appropriate resources as per the design specifications. Once all the resources are mapped, it will do routing. All the connections will be interconnected. Then we will do one timing analysis. We will verify that the design meets the timing or not. So the timing analysis, you will get a report here itself. This is a project summary, right? Here you have a category like timing and power. Here you will get after implementation. But right now I have not run. That's why the panels are empty. Actually, for running all this process, it generally takes 10 to 20 minutes, depending upon hardware design complexity and system performance. But right now, due to time constraints, I'm not running. I will show you the implementation, which I have run beforehand. So after timing analysis, we will do bitstream generation. That is what the configuration file I said, right? In this configuration file, the key hardware information related data will be available. That data will go inside FPGA and it will configure all the resources and it will build the appropriate circuit what we have designed. Once the circuit is done, bitstream file is done, we will load that into the FPGA, and then after loading it into the FPGA, the actual hardware, whatever we have built, that will be implemented. Now, how to test and validate it? Since we have connected this debug IP core, right? VIO IP core. Using that, we will try to debug and check whether it is working as per the intended functionality or not. If at all at the hardware level it started to fail, but when you have done the simulation it has passed, then what you have to do is like you have to go back and do some changes, and then you have to match your hardware result with the simulation result, and both the results should match with your software level model. Then only it's like a complete proof of concept, like the intended functionality you have successfully implemented on FPGA. If at all if you face any errors or warnings, or any functional mismatch, you have to iterate all the above steps whatever we have checked in the FPGA design flow in order to get the proper design. Now what I will do is like I will close this design from here. Actually, it will reach for generation. It will take more time. So I have already generated one design that I will use it for illustration. Now you can see all the panel windows, all some key informations are available. Here you have timing information. Here you have power information, and this is the hardware implementation. So FPGAs have basic building blocks like lookup tables, RAM, flip-flops, input, outputs, buffers, and clock. So these are the available things in FPGA, and these are the utilized things. So in this way, the area results and reports are made available. This is the power report. Like my design is working at 218 milliwatt, and this is the timing information. Version A2 slack 4.8. Actually, this design I have done for 100 megahertz. This is the constraints file. So clock, as I told you, I have connected to the onboard crystal oscillator. Reset button, I connected to a push button. And if you open the block design, it is more or like the same what I have done earlier in the demonstration. So this design, right? So we have validated, we have generated a top level wrapper. This is my top level wrapper. This is a thing. And inside you have all the proprietary Xilinx based IPs are used, and my own IP like pseudo random binary sequence generator, everything integrated into one main file. This is a top file I'm talking about. Once this is done, we do synthesis. If synthesis is passed, there are no errors and warnings, we proceed with implementation. If implementation is also fine, then we finally generate a bitstream. So synthesis like RTL level to gate level description will get from while doing implementation, the gate level netlist will be converted into FPGA netlist. And when you generate the bitstream file, the configuration file will be generated. Now I will just connect my hardware and I will show you the demonstration. Here on the right hand side, you can see the write bit stream is also completed. So all my files are ready. So now I'll just program my hardware and I will just show you the outputs. So just 1 minute, I will set up my hardware. Yeah, we can wind it up in another 5 more minutes. I just wanted to show the output. I have connected the programming cable. Okay. I have just connected the programming cable. This is the power cable connecting. Yeah, I'm turning on the switch. So my hardware board is connected, powered on. So now what you have to do is like I have to click on open hardware manager. So now the Vivado will try to connect to the board. Here open target and click on auto connect. So it will scan the ports and it will try to identify what is the board connected to the host PC. So to the host PC, I connected my Z board. It has identified successfully. Uh, yes, connection has been established. Now click on program device. So here there are two configuration files. One is related to your own hardware. Other one is like the extra peripherals like debug IP cores that we have added only just for the sake of sending data to the hardware and receiving the data and visualizing it. So that is not the actual part of our design. Our design is like scrambler. But directly if we implement a scrambler, we cannot be able to pass the input and get the output. So around the scrambler, we have built other peripherals from the Xilinx side. Those are called Xilinx IP cores, only to send the data to our scrambler and get the data from the scrambler and visualize it. So there will be two files separately. These two files will program it. It is programming my FPGA. Once the programming is done, a blue color LED will blink on the board. You can see. Now what happened? Automatically the debug course has already opened to my last test case what I have run. So initially, first what we have to do, we have to give the CIN90 value. So currently I gave the CIN90 value as in hexadecimal 3F000A. This value, I think you have to do conversion and check what is the exact value. And message data, I kept it as like 23. The scrambling sequence output is 0. There's nothing coming. So that's why the output of the scrambler is also 23 in hexadecimal. Now what I'm doing is like the done signal is 0. You can see here the done is 0. That means scrambling sequence is not yet generated. So I am triggering my uh, pulse generator to send a starting pulse to my pseudo random binary sequence generator so that it will generate a scrambling sequence. So once I make this as 1, you can see the done is high. So it indicates like scrambling sequence has been generated and my scrambling sequence output is like A4. Now you can see uh, my data, I gave it like hexadecimal 23. That means 0 0 1 0 0 0 1 1. And depending on my CNIIT value, I got the scrambling output as A4. A4. This is my scrambling sequence. A4 means 1 0 1 0 0 1 0 0. Now, based on this, if we do a scrambling operation, 0 1 1 0 0 0 1 1 0 0 0 0 0 0 0 0 1 1 1 0 1 1 0 1. It's an XOR operation. So this is nothing but 8 7 in hexadecimal. So here I'm getting the scrambled output as 8 7. Now at the receiver end, that also we have added, right? So we use the same scrambling sequence 1 0 1 0 0 1 0 0. We perform XOR over here. Earlier we performed XOR here, now here. So 1 1 0 0 0 0 0 1 1 0 0 0 0 0 0 1 1 0 1 0 1 1 0 1. So we got same as our original message sequence 0 0 1 0 0 0 1 1, that is 2 3 of 16. So this successfully shows that whatever the scrambling circuit that we have implemented on the FPGA, it is able to take a code word of 8 bits. It is generating a scrambling sequence of 8 bits, and it is doing the scrambling operation. This descrambling we have done only to verify, but actually we have implemented a scrambler. In the receiver side also, we follow the same technique to implement a descrambler also. So ultimately what we have done, we have taken one communication 5G communication component block in the transmit chain or a receive chain, and then we try to implement it on the FPGA, and this block is processing at the physical layer of the 5G communication. So we call it as 5G physical layer communication component implementation on FPGA. This is just a simple illustration to give you a better idea like how the communication system blocks are being implemented on FPGA. I hope this session is informative and you might have got a basic idea of the outline, how the industrial standard based FPGA based implementation of 5G communication systems takes place. I have considered a very simple example to show like the design flow and implementation flow. And from at this point, now I conclude my presentation. I thank all the participants for your active participation. If there are any doubts, I can just answer, or else we can just wind up the session. I hope you all have informative sessions in this FDP, and also there is some more interesting sessions coming up in the next few days. Over to you, sir. Hello.
Yes, sir. Yes, sir. Yes, yes sir. Am I audible, sir?
Yes, yes, audible, sir.
Sir, good afternoon, sir. I'm very much thankful to Dr. N. Sai Srinivas, sir, for accepting our invitation. The sir was well explained the topic on hands-on demo 5G physical layer processing on the FPGA. To be specific, the scrambler and descrambler for 5G application. So once again, I'm very much thankful, sir, accepting our invitation.
Yeah, thank you very much, sir,
Yes, sir, and
for
please,
giving this opportunity.
yes, sir, please hold on that video, sir. Means, now
Yeah,
we are
yeah, yeah.
taking the virtual photo with you, sir.
Okay, okay, sure.